Okay, welcome back. We're going to keep going with section 4.1 now. Okay, just to help out, I've rewritten the definition of a random variable here. Sorry about the barking in the background. A neighbor's dog is going a bit nuts. We've got one sort of simple fact from this definition is that, if x from omega to omega dash and y from omega dash to omega dash dash are random variables, where sort of I'm not writing the sigma algebras, but you would have like an f dash, f dash, f dash dash. If these two are random variables, then their composition is a random variable. Then y of x from omega to omega dash dash is a random variable. Now let's just think about why this is true. Okay, well, if you've got a set in omega dash dash, since y is a random variable, you pull it back through here, you get an event. Sorry, I think I may have said something wrong there. If you have an event in f dash dash, then you pull it back through y, you're going to get an event in f dash. If you've got an event in f dash and you pull it back through x, you've got an event in f, because x and y are random variables, and therefore you pull an event in f dash dash back through this composition, you're going to get an event in f. Okay, and that's what it means to be a random variable. So yes, the composition of random variables is itself a random variable. Okay. So now I want to introduce a lemma. So this is a sort of leading towards an alternative view of random variables. So lemma: if x from a set omega to, let's let omega be a set and omega dash f dash be an event space, then every function x from omega to omega dash defines a sigma algebra. Okay, and how? Maybe I should say, rather than defines a sigma algebra, we'll just reword this a bit. So then for every x which goes from omega to omega dash, the set sigma x, which is defined to be the collection of sets x in a dash for a dash in the sigma algebra on omega dash, is a sigma algebra. Okay, and this is a very easy lemma to check, pretty much because these sets here are all based on something which you already know is a sigma algebra, and then you use properties of pre-images under sort of unions and intersections and complements. Okay, and we denote this set here, we call this sigma of x the sigma algebra generated by x, Okay, and now note the distinction. So we've previously seen for a collection of subsets, we've also got notation for for a collection of subsets of omega. We recall that we've got sigma of G is sigma algebra generated by G. Okay, now this could be a little worrying because these notations are practically the same. So there's a reason they're practically the same. It's because what we do here is very similar to what we do here. But you shouldn't really get these confused because, well, this X is a map between things, while G is a collection of subsets of omega. So hopefully this notation won't be too confusing. Now, why do we use this notation? Well, let's just find the right spot in the notes, sorry. Okay, well, yeah, pretty much the idea is that sigma of X is the smallest sigma algebra on omega such that X from omega sigma X to omega dash with F dash is a random variable. Okay, and you can check this very easily because, well, for X to be a random variable, you need all these sets to be in the sigma algebra. Okay, just by definition. And then, well, you can check that all these sets, the collection of all these sets does actually form a sigma algebra, and therefore it's the smallest sigma algebra, which makes X a random variable. Okay, so now, similar to how we had sort of extension theorems for probability measures and stuff like that, we've got a simplified way to check if a random variable is, well, if a map is a random variable. So we have the following proposition. So we've got two event spaces, as before. Okay, and we've got some X from omega to omega dash, and we've got some, well, yeah, let's just leave it there. Okay, and then we've got some G dash contained in F dash such that the sigma algebra generated by G dash is all of F dash. Okay, so we've got some generating set. Then X is a random variable. Well, if and only if it satisfies the properties on the generating set. Okay, if and only if X in A dash is in F for all A dash in G. Okay, the restriction being here that you only need to consider A dash in G, and this is going to be a very helpful theorem, as we've seen. Well, very helpful proposition, as we've seen even in the case of the real numbers, the Borel sigma algebra. So if you were to take this to be R, this to be B1. Well, sets in here are very hard to get our hands on explicitly, but there's a very nice collection of generating sets. There are many very nice collections of generating sets. Okay, well, so this is going to give us a much easier thing to check that a function is a random variable. Okay, and let's prove it. Okay, well, on the one hand, x random variable clearly implies that x in a dash is in f for all a dash in G, and y, well, since G is a subset of f dash. Oh, sorry, I've called it dash previously. Okay, so that's the easy direction. Alternatively, we have the following. So for other implication, we'll look at the set f dash dash, and this contains all the sets in omega dash such that x in a dash is in f. Okay, now it's straightforward to check that this f dash is a sigma algebra. I mean, f dash dash is a sigma algebra. So claim f dash dash is a sigma algebra. Okay, and this is because, well, I'll just leave this to homework. Now, another claim is that, well, G is a subset of f dash dash. This is immediate because, well, by assumption, we know that for any a dash in G dash, sorry, I missed it again. For any a dash in G dash, this set is in F. Okay, but then we find that, well, F dash dash contains G dash. Well, this means that the sigma algebra generated by G dash is contained in F dash dash. By definition, this sigma algebra is the smallest that contains G dash, and F dash dash is itself a sigma algebra. Okay, but this is exactly F dash by assumption. Okay, and then we find, well, just manipulating this definition, we find that for any a dash in F dash, x in a dash is in F. So this implies that x is measurable, that x is a random variable. Okay, maybe I'll just write that out a bit more clearly. I think that was a bit quick. Okay, so from here we find that, well, for all a dash in F dash, a dash is in F dash dash, which is equal to the set of, well, subsets of, and this by definition of F dash dash implies that x in a dash is in F. Okay, skipping the middle term, we find that x is a random variable by definition. Okay, and that's the end of the proof. Okay, so as I've said, this is going to be very helpful. So from here we get another example. Okay, if omega dash f dash is just, well, the real numbers with the Borel sigma algebra, one-dimensional Borel sigma algebra, function x from omega to r is a random variable if and only if x less than or equal to c, by which I mean the set x in negative infinity to c is in F. Sorry, this should really be here. Okay, and this is a very easy condition to check. Furthermore, you can put a bit more work in and check that if omega dash is in fact a subset of R and f dash is the Borel sigma algebra restricted to omega dash, then continuous functions from omega dash to R are random variables. Okay, and we'll leave that lecture there. Okay, thank you.